Welcome back, everyone. And today we're going to finally do something that we kind of started a little bit. I mean, we kind of put placeholders for a long time ago when we refactored fungi. Now we're going to actually finally flesh it out. We're going to start working on implementing a screen graph, also known as transformation hierarchy. And more layman's terms, it's really just parent-child relationships between our renderables. In case you don't get what it all means, is basically parent-child relationship. Here's just tons of images you can find on Google image search to kind of illustrate. It's basically just a tree. You have your world, you have a house in your world. In your house, you have your door, you have your window. It's just layers upon layers of objects that are connected together in a parent-child relationship. Now, why do we need a screen graph? It's a screen graph in general by itself is useless for the most part, but when you actually take the second name for it, would be a transformation hierarchy, then it becomes now it starts to make sense of what it's for. The idea is the transform of the parent node will then get carried down to the child node, and that child node's transformation gets carried down to its children, and so forth and so on. So the idea is that if I move the world 10 units to the left, the child will also move 10 units to the left, and so forth. Now the thing is, now we're going to start building layers. So now we're going to have something called world space and local space. Local space, every object has its own local space. It's transformation based on origin. World space is after you apply the matrix. So once you apply the matrix transformation to all your vertices, you transform out of local space into world space. You can think about what the GPU is doing when we're pushing it to the GPU and rendering it with a shader. We're going through every single vertex and we're transforming its location to a new location. So that's what I mean between local space and world space. Local space is basically like no transformation. World space is some kind of transformation is done. So I'm trying to see any other way I can explain it. So, like I said, like the really big example of it really is that, let's say if I move the world 5 pixels to the left, and the local space or the local space for the house is 3 pixels. So when you combine the two matrices together, or the two transformations, the house will actually be 8 pixels to the left. I hope I lost track. So yeah, the world is 5 to the left, the house is 3 to the left, so it kind of just adds up. So now the house is actually located in the world space of 8 pixels to the left, but its local space is only 3 pixels. It becomes world space because now you're applying the parent transformation. The root node of the tree, or the topmost parent, its world space is also its local space, because it has no parent to transform it even another step forward, or another step of movement and rotation and scale. So just keep that in mind. The top node, or if you're at the top part of your tree, your local space is your world space. Things become a little bit more complicated when you start dealing with children, because then that local space could be different from its world space. If the world space has no transformation, then the child's world space and local space would be the same. They're equal. So just keep that in mind. Now we're going to start dealing with spaces, world and local. So we're going to continue on where we left off before, where we kind of built a little road and we have our little planet. Right now, let me just quickly show you. We're going to move our world. Right? Refresh. As you can see, our world moved, but our road did not. So in the end, when we have all our code in place, we're gonna when we move this world, we want the road to automatically move with the world. So because the road would be a child node to the world object, this little planet sphere. So that's what we want to implement today. So let's go to the core. We're going to start doing some changes. And it's actually not a lot of code to really implement because we kind of already had a lot of it to start with. So the new thing we're going to do is add world matrix. Excuse me. Just another matrix, that we're going to keep track of. We already had children and we already had parents. Like I said, when we refactored, we kind of start implementing some of it, but it was kind of just a skeleton. We had no functionality. It was kind of just placeholders. Another thing I'm doing is I'm moving visible to transform. Visible is actually part of our renderable. I'm taking it out of renderable and putting in transform. Now you might be asking, why am I doing that? Because transform is now going to be usable as like a folder or as an empty. I think in Unity they're called empties. So this way we can have like just a transform, but it's not renderable. So we can apply certain things to it. Like let's say I want to create an empty called a house, and then inside the house I parent child a bunch of walls. So when I move the transform, like the parent transform, which is not a renderable, it will move all its children in relation to that transform. So that's the reason why I'm applying it visible to it, because this way I can now control visibility of the transform in general. So anything that that inherits transform is automatically something that can be visible and invisible. So like I said, transform is going to work as an empty or as a folder, or just kind of like this box that's not rendered, but its transformation can be applied to its children. There's a lot, when we work in the future, we'll start dealing with it more, but it's kind of a useful thing to have when I was learning Unity to help organize. All right, so we got visible, we got the world matrix, we got children, we got parent. Fine, next. What's the next change? Just get parent and set parent. So, you pass in the parent. If the parent is not null, you call the parent, you tell it, hey, remove me from your list. Because if we're changing parents, we want to, remove ourselves from our previous parent. Because we don't want to be referenced to two different parents, because then you'll have like rendering issues. Like then you'll have this child will have two matrices applied to it because it has might have two parents. So that's what you do. So this parent remove the current parent, just remove me from you, and then if parent equals null, add child. P becomes null because remove child from the parent would actually apply null to parent itself. It's kind of a little hack, but it's I'll show you in a second. Let's see. Let me go to add child. Now, this is the reason why I say it's kind of a hacky. So when we set parent, we say parent add child. So if this was a parent, it would go check to see if it's part of the child, and then it takes the child's private parent. See, mind you, if this was an object-oriented, like if objects were allowed to have private and public, this ideally would be private. I should not be able to access this. outside. So this is actually bad object-oriented design. Like I know it's bad because the idea of object-oriented is that every class should be self-contained, and its private members or its private fields should not be directly accessible from another object. So that's what I'm doing. That even though I have an underscore marked as basically this is private, and when you want to modify a parent, you should be using these parent objects, I'm actually going to have the parent directly modify a private field. And like I said, that's really not something you should do. But the reason why I'm doing this because I want to be able to apply parent just by just assigning a parent or by using add or child. Technically, I can only do one or the other because if I try to do both without this little hack, you kind of create this infinite loop. Because let's say I set the parent and I tell parent remove child, and then remove child calls parent, and then comes back here again, and it ends up creating this kind of weird loop of things that running, and then it kind of can cause issues. So that's the reason why I did the hack. So this way I don't create that loop happening. So I just want to warn you, what I'm doing is not necessarily the right way. It works, it does the job, it does exactly what you want. But if you're going to be an object-oriented programmer and follow some of the unwritten rules or what's the best best practices, you should not do this. But again, because I wanted to be able to use add child and remove child or do it like parent, because I think in Unity there is no add child or remove child. I think it's just parent. So you just assign yourself as a parent, or you just say parent equals no, and it automatically unassigns you. Like I said, I want to be able to do both. I want to use the function, or I want to be able to kind of just apply it parent directly. So by doing this little hack, I can actually have both functionality. And as I'm developing, I can figure out what feels more comfortable program-wise. Do I want to use the add and remove child function, or is it just better just to say this is the parent, or if I want to remove the parent, I just say null. Instead of having two functions, I just have this get and setter for parent. So when I actually probably create the framework, when I refactor again, I'll pick one of the methods to really use. But for now, I'm going to play with both to see what feels comfortable to me as a developer. So this little hack allows me to use both and still be functional. So now that the long-winded reason why, and like I said, I don't want you guys to think this is appropriate. I just want you guys to know the best practices. Like, you shouldn't do this. You can if you need to, because if you want to do something, but you shouldn't if you really, really don't need to. All right. So now I got that little programming warning because I don't want to make you guys bad developers. Do as I say, not as I do. Now, the next thing we got to change is we're going to get rid of our old update matrix, which is very simple. It just checks to see if it's been modified. It's using the dirty design pattern. So like if one of our values have been modified, then we create our transformation again, and then we set everything back to false. Now we need to do the update matrix slightly differently. Our new update matrix has a new attribute called force world update. Now, why is this here? The reason why it's here is because when we're rendering, we want to be able to force this thing to update. By using the old function, if the parent modified itself and there's a new matrix for the parent, and I say to come here update matrix, but the child did not modify its values, it will never go grab the world matrix, because there'll be no way, unless I'm going to go, because the world matrix already updated itself and has reset its is modified things. So during the rendering, we're going to render everything from parent to child. So and we have to update our renderer to support that. So let's say let's say the parent's position was modified. Now every child that we render from that parent, we have to tell it, you have to update your world matrix. So let's see. So like I said, it uses the dirty design pattern. So if our local matrix needs updating, it updates it. So if it's not dirty, and if we're don't need to do a force update, we just return false. We're now returning true or false, because we're now telling the renderer if the matrix did update. If the matrix did not update, like I said, return false, the force world update value will not be true for the children of this specific object that I'm currently rendering. So I return true if either case, if the local or world matrix change in any way, I return true, because that means all the children for this object needs to be forced to update. So if it's not dirty, if we're not forcing it, we're good. No updates are required. If it's dirty, we're going to update our local matrix. Our local matrix is good. Now, if we don't have a parent, or if we do have a parent, so it's not equal to null, we're going to multiply our parent's world matrix by our local matrix, which would then get saved into our world matrix. So parents and local, and it's just multiply. So that's kind of like how you add matrices together. You actually just multiply it together. So like I say, if I want to transform, do one transformation, do another transformation, you actually multiply to actually apply the addition in the matrix form. If we don't have a parent, like if this is the root parent, then the world matrix gets a copy of our local matrix. The data just gets copied over. So, all right. So that's really the gist of it. And like I said, we return true if we updated it. So yeah. Next, we did the child. Nothing too complicated. If it exists, or if it does not exist in the list, then we can add it. And I guess the same thing with the child. If it does exist, remove it from the array. All right, what's next? Like I said, we got rid of visible from renderable, because now it's part of transform. Now we're going to our matrix 4 function. Remember, if the parent does not have, like if your renderable doesn't have a parent, we just copy. Here's our copy function. We need a new copy function. All it is a loop, and it just copies the data from one to the other. Fine, next. Now we're pretty much near the end of our changes for core, and we're going to start updating our renderable. So here's our main render call. As you can see, this is where we were looping through our scene array. That has been commented out, and now we're going to push the array to a new function called process list. And we're going to say false, because that false is the first force world update. Since it's going to be the root elements in our rendering engine, or it's the root elements. Right now we're going to start processing all the parents in that we have listed in our scene. So we don't need to force the update. If its local data is dirty, then it will auto update by itself. So it does not need to be forced at all. So we're going to process the array. So we pass in the array, and we have that. And it kind of pretty much is a lot of the same stuff. We check to see if it's visible. We continue. We do the update matrix. We push in forced. But like I said, since it's the initial start, it's going to be false. So we're not going to force it. And we check to see if it's updated. We check to see if the object that we're rendering has a draw event. Because remember, now we're going to be able to put transforms into our scene to act as empties or parents or boxes or folders or whatever, or just containers. So if there's no draw, if there is a draw event, we prepare it and we draw it, and then we say it's been rendered. And now if it's a transform or a renderable or a camera, a light, whatever, we're going to check to see if it has a children length. And if the children length is greater than 0, then we call this function again. And instead of passing in our scene array, we're going to pass in our children array. And then we're going to say is updated or force update. So if either one of these are true, it returns true. So then the process list going forward, as deep as it goes per child, child of a child of a child of a child, that true value will be pushed down all the way to the very end. That means so if the very tippy top element in our tree or root element in our tree had its local matrix updated, then that value will be pushed throughout all the children that exist underneath it to the very bottom. So everything kind of just cascades, everything kind of just adds up. And that's it. And this function is just recursive. So we draw the parent, then we tell it to draw the children. And what else? And the only other thing is in prepare next, we got rid of this line because this is when we used to do an update matrix. Now we just pull out the world matrix. We don't call a function. We just pull out its world matrix and we're done. And that should that handles everything. Now, the approach I did using recursive and having the renderer kind of handle all the parent-child rendering is just one of many ways you can go about this. You can go about a lot of different ways to do parent-child screen graph rendering. One way I've read about it is that, let's say we have a renderable. That renderable when we tell it to draw, it will then call its children's draw events, and they'll cascade that way. Now, the thing is, I didn't want to apply it that way, especially since my transform does not have a draw event, and I'm going to have other objects that extend the transform, like light and cameras, and those don't have draw events. So I can't really go that direction. On top of that, I don't like the idea of my renderable handling to draw its children. I like the idea where the renderable really just takes care of itself. And like I said, that's kind of like the good thing about, or not the good thing, kind of like the approach of object-oriented language. Each object is supposed to be its own self-contained box that has access to the data inside of it. You have your getters and your setters, methods and functions or whatnot. So that is kind of like, that's the approach I kind of went, where I wanted my renderables to be self-contained and only worry about itself. I'll have the render function deal how to handle that hierarchy. So this way, because I know many lessons ago when we were doing VR, we end up creating a whole new renderer function to handle rendering VR stuff. So I like the idea that we can just go around and just recreate the renderer any way we need to for the application, and this way our renderable objects stay the same. So this way, depending on the application, depending on the game, we can design our renderable to render whatever way we kind of makes more sense. So this way, we keep the children components kind of doing its own little thing. So hopefully I explained that right. But like I said, if you go to research screen graphs, you're going to find there's a lot of different ways to go about it. So this is not the only way to do it. This is what makes sense for me and what makes sense for fungi. But like I said, in the course of building this, your direction might change. You might learn something new. Like in the very beginning, I thought I didn't need materials. 15 lessons down the line, 3 or 4 months down the line, you start realizing, you know what, I actually do need materials. I need a materials object. So you never know. Things could change. So, but like I said, this works. This is one of the methods that I did read about, just have a renderable kind of just handle it. And that's the direction I do prefer to do anyway for now. But like I said, that your renderable or how you render your screen graph can be different. It really depends on your style. Maybe you want the renderer to render its children. Maybe you have a really cool way of rendering and you have the renderable actually doing it itself instead of having this outside object managing everything. Because like this render becomes its own little system. So like if you want the renderable to be its own system that handles itself, that's fine. Or this way it's like two systems. You have the renderable objects, they kind of deal with themselves, and they have the renderer that knows how to use those objects to render in a certain way to kind of to accomplish certain things. Yeah, I think I probably talked too much about that, but I just want you guys to have that information to really realize that this is not the de facto way of doing it. This is just one of many methods. So for continuing education, just look up screen graphs. You'll find tons of information about it. There's a lot of theory behind it. Like I said, it's just a lot of ideas of how to render objects that are put together in parent-child relationships. And on top of that, the way I did parent-child relationships, that's not the only way to do it. Having a parent reference and then an array of children, that is one of many ways. There's one way with just one huge flat array. Then there's with other objects that kind of binds the connections. Like I said, there's like so many different ways you can look up on how to manage the data structures of parent-child relationships. Like I said, the way I did it right now is like the simplest way to go about it. It's probably not the most efficient way, because then you're because you have to go from parent to child, parent to child, parent to child. If performance and speed is important, then like a flat, huge array of a couple of different arrays and having the data kind of linked together might process faster. Like if you're dealing with like hundreds or millions of objects on screen, and you need that extra, like all those memory lookups are slowing you down. And memory lookups is not something you are concerned about in all on especially JavaScript, because JavaScript is not really a program. Like if you're programming C++ and you're trying to squeeze out every possible ounce of performance in your game, like you're literally down to the millisecond, you're trying to squeeze as much out as you can. Just pulling information, just accessing memory can take time. So if you structure your data in a way where you eliminate a certain amount of memory lookups, you might speed things up. Like the way I have an array, I have to look up the index first, then I have to find the item in memory that the index points to. So there's kind of two memory lookups. There's a data structure, I forget it's called, damn it. Oh, and I had it in my mind. Linked lists. You can have a linked list. It's a different data structure. It's kind of like an array, but different. And as you go from one item to the next, you don't have to do the index lookup. So let's say if you're going through a million objects, it would actually be faster to use a linked list than an array. Now there's pros and cons with linked lists and arrays. It depends on what you're trying to do with them. But like I said, parent-child relationships can be structured in a lot of different ways and using a lot of different types of data structures. And depending on how much, it depends on how much performance you're trying to push out. Like, linked list requires you to do handle the data differently and organize it differently. but by doing so, you might squeeze out extra performance that actually can, maybe shave off a few milliseconds to get you an extra couple of frames per second boost. But like I said, that's something you can really do with C++. I'm sure you can kind of get some performance improvements by doing things like that, but I don't know. This is JavaScript, and I never really expect to go too far with the JavaScript thing. Like, this is really just meant as a quick and easy way to prototype and learn OpenGL. So this way, once you understand it fully, you can then go to C# or Golang or whatever language you want to use, like for desktop development, to really make real games. You can make real games with WebGL. It's just, I think you'll never get as much performance as you would to something that's more, like you probably get better performance out of Java as opposed to JavaScript. It's just based on how the language is built. It's not built for speed. It's built for accessibility and usage. Okay, so I probably took a huge tangent. So let's go back to our code, and so everything's already set up. So if I go here, make sure everything's cool, everything's nice and copacetic. So as you can see, our model 2 is our road, and I just push it to the scene. So now I'm going to comment it out. It's no longer part of our scene, but now I'm going to apply it to our parent, and our parent is so we're going to say model 2 is parent is a model, which is our sphere. I know I should call it GSphere and GRoad, but we're prototyping. We'll optimize later on when the scene is nearly complete. I got something in my eye. So yes, I make the parent. I'm doing it the way Unity does it, just because it seems easy. It's less code, and I don't know. I like get and setters as opposed to using methods. So we refresh. Now the road is where the sphere is. It moved up. So let's see. So I can apply rotation. So I'm gonna rotate it by 90 degrees. And now it's 90 degrees. So now, mind you, this the road has no rotation at all. There's no rotation. Its local space rotation values are all 0. But the rotation value of the parent is 90 degrees, which then cascades to the children with our use of our renderer. And we can also apply scale as well. I can, by scaling the parent, I can scale its children. Ta-da! And to show you local space, we can move our model or a road independently. But as you see, it's still rotating 90 degrees plus its transformation. If I want to comment that out and do rotation, there you go. So as you can see, now I gave the road itself some rotation. So it is being rotated by 90 degrees, and then its local rotation, say, to move it negative 45 degrees back. So now it's at 45 degrees, the in-between space between its natural orientation and its parent orientation, because its parent is 90, and the local wants it to be negative 45. But see, because I'm taken away, but I can actually go the other direction. I can just end up adding onto it. So boom, now it's, so that's 90 plus 45, so that's 135 degrees. So its actual rotation from its origin is really 135 degrees because it adds up. That 90 degrees plus that 45 degrees I just added to it. And that is pretty much it. So I leave it nice and small. You know what? Make it big. I want to make it big. I want to leave it big. I don't want to see it scaled anymore. So there is our parent-child relationships, our transformation hierarchy. Parent, you know, our screen graph. Those are all the same thing. But now we're going to have a little bit of fun. So we're going to change the rotation on our unrender function. So now we're going to go boom. So we're going to rotate. Let's see, we're rotating our G model. So we're rotating the sphere, and since that is a child or a parent, or sorry, that is a child of the sphere, it rotates with it. Now I can just show you that by simply removing it from the parent, then making it a root element in our scene. Now it doesn't rotate because it's not a child. So the matrix of its transformation matrix does not cascade down. So now we're going to make it a child again, right? So I'm going to refresh again. So now they rotate together because it's coming together. Now in relation. So our sphere is rotating 45 degrees per second. So every second that passes, we're rotating 45 degrees. It adds up, you know, it keeps rotating. Our model 2, which is our road, also rotates by 45 degrees for every second because of its parent. But now I'm going to apply its a local rotation to the road. So the road is going to be traveling at 45 degrees plus 60 degrees. So it's going to be traveling 105 degrees per second. So when we do a refresh, you will see that our sphere is still rotating at 45 degrees a second, and our road is going 105. And just to prove it, I'm going to make them both go at 45 degrees. That means our road will be traveling 90 degrees a second. So it's still going ahead of the sphere, just to prove that, you know, the rotation is independent, or it's not independent. They're adding up. Because now, if I want to be a pain in the butt, I can say, let's see if this works. I haven't tested this out. In theory, if I'm going 45 degrees that way, and then the child wants to go 45 degrees that way, it should probably stand still or still travel. It'll stand still. So there you go. So I'm rotating. The sphere is telling the road to go that way 45 degrees per second, and the road wants to go 45 degrees in the opposite direction per second, and it cancels out and it becomes neutral again. So, but I still prefer it to be at 60 degrees because that's where it looks like it's fun. There you go. And now you can rotate. We got the camera controller. We can see it, this rotate, zoom in and out. Yeah. And there it is. And there you go. We went through a bunch of tests, playing around with the parent-child relationship and having all the matrices, transformation matrices, kind of adding up and, you know, fighting itself. Because, you know, we set it up to fight it on purpose, just to prove a point, really. So, yeah, that's pretty much it. This is great. This allows you to do a lot of things. you can build a car, apply wheels to it, and you can have the wheels be children of the car, and the wheels can rotate independently, to make it look like it's moving, and the car stays perfectly still. And the beautiful thing is you can have the wheels rotate, and then you can tell which are children to the car, and you can tell the car to move. So the wheels will rotate locally, and when you move the car, you move the children along with it, like this example, and you can then design a car. Like, this allows you to get away with that functionality really easy. Else, if you didn't have screen graphs or a parent-child hierarchy or a transformation thingy going on, you would have to rotate the wheels and then translate them to where they should be on where the car currently is. By doing this parent-child relationship, you don't have to worry about that. You just have to worry about the wheel rotating in its place, and then the car hull or the car frame would actually move the wheels for you. So you can kind of segregate all the functionality, and at the end everything gets rendered together and create the effect that you're actually trying to accomplish. Like I said, with this example, I'm making one rotate and I'm making the other rotate a little bit faster, but when it all adds up, the child is rotating much faster compared to its parent. It's kind of like if you're going to see a lot of scene graph examples, they always talk about planets. You have the sun, and then you have the Earth that rotates around the sun. Then you have the moon that rotates around the Earth, which kind of rotates around the sun, but because the Earth is rotating around the sun, the moon rotates around the sun too, but only in relationship to the Earth. So that's the example you will see a lot of if you look up scene graphs. But like I said, we're making one planet and we have a little ring, so this was a pretty good way to illustrate parent-child relationships. Another great thing for screen graphs, or the idea of hierarchy transformations, once we're done with King Sky's planet, we're going to move into bone animations. And bone animations works the exact same way. If you're dealing with a humanoid, you always start with like the hip bone, and then you have your leg bones, your pelvic, your chest, your arms, your legs. All that kind of creates a power-child relationship. Every bone becomes a child of the previous bone. So the root bone is your pelvic part of the model. That's the part where you kind of end up moving everything around, and then you have all the other bones. So if I rotate my arm, my shoulder bone, it would automatically rotate my arm and my hand vertices as well, just like this. So what we're doing right now is really a kind of precursor to bone animations, because if you can understand doing this, then bone animations are actually half done. Because like I said, first half of bone animations, or I think it's also called skinning, is really just the parent-child matrix transformations. And as long as you have a method of cascading the matrix down to the deepest child, and having the data update itself correctly, you can do it. The only other part that's related to skinning or bone animations is applying weight to the vertices. So you can each vertice in your model is assigned to a bone, and how much of that bone influences its transformation. So the neck, around your neck, will have two bones that really manipulate it. You have the shoulder, or your your torso bone, and your head bone, and they both can manipulate your neck stuff. So the vertices around that create the neck in your 3D model might be 50% applied to your head bone and 50% applied to your torso bone. So that's so that's kind of like the more advanced parent-child relationship, is when you can actually have more than one parent. And then the way you deal with it is you have to create weights. With this example, I really try to avoid multiple parents because we're not dealing with weights and everything else. But that will be a more advanced version of what we're doing today. We did today. So I just kind of wanted to just add to it, like something you can research further if you're really interested in just the general topic of transformation hierarchies, because screen graph is this and bone animations is the same thing but different, because you have to deal with weights. That's why I'm giving you more than one name, because the subjects are very similar and they're just different things that are used for, like I said. So yeah, that's it. That is the end of today's lesson. This should have been a quick, short one, but I spent a lot of time really explaining a lot of things. I know that today was a lot of talking and probably very little code changes, because overall the code isn't really not that complicated. But there's a lot of theory to it. So hopefully you kind of understand, play with it, mess around with it. Use a transform to create an empty and then apply the sphere and the row to it. See if you can manipulate it that way. Or create multiple spheres and create a kind of rotation. Set up the sun, set up the earth, set up the moon. You now have officially all the pieces you need to actually build a solar system type 3D model thing. Like I said, with the screen graphs, with the sphere, and all our matrix transformations, very easy to build a solar system now. So that's it could be a challenge for you guys, just to mess around to really get the grasp of the screen graph functionality. So I think that's about it. This video is late. I should have recorded this last week, but I was busy trying to create dynamic trees. That took me like a week to really get right. So I really was focusing more on, I guess, the next lesson to record this lesson. But so far I can say that the tree is starting to form itself fairly well. And I'm not using certain systems. Never mind. I'll just explain it in the video. But let's say I'm making a tree and it looks pretty neat. And my desktop computer does not have a copy of the source code. So I would like to quickly show it to you, because I'm kind of really proud of it, because I built it from scratch without using L systems or anything else. That lesson will be probably long because there's a lot I'm using. So like and subscribe if you have any questions, if you have any suggestions or any requests for additional videos, feel free to comment. So that's it. I hope you're having fun, because this is great. We're starting to get to some advanced stuff. And I really can't wait till the next lesson. We do trees. And then I think from there, I think that might be it. And then I'll probably quickly put together King's Kai's planet. And then we can move on to bone animations and start really doing some really fun stuff. So I guess I'll see you guys in the next lesson. See ya.